Here are solutions to homework set number 12 for ECE 461-6061 control systems. This homework set looks at Bode plots, Nichols charts, gain and lead compensation. Now the first problem is the Jeopardy question. What's the question? Here's the gain versus frequency. What's the transfer function? To do that, the trick is to draw in your asymptotes. I want to draw in straight line asymptotes that are multiples of 20 dB per decade. So here's one right here, flat. Over here, this is 1 decade. Here's 20 dB per decade. Here's 40 dB per decade. Here's 60 dB per decade. This looks like the right slope. I can then draw 40 dB per decade in here, then a 20 dB per decade. You got to get these slopes right. They've got to be multiples of 20 dB per decade, because 20 dB is a pole. 10 dB is half a pole. A pole is a derivative, so I can do 1 derivative, 2 derivatives, 3 derivatives. I don't know how to do half a derivative. So that's what 10 dB per decade means, half a derivative. You can't do that. So keep these at multiples of 20. Where they intersect are your poles. That's why they're called corner frequencies. So doing that, here's the first asymptote I drew, 0 dB per decade. This one's at minus 20, minus 40, minus 60. Where they intersect, your corner frequency is your pole. So I've got a pole right about here, about 1.8 radians per second, one here, about 7 radians per second, and one here, about 22 radians per second. So there's the form of my filter. To find K, pick a frequency and match the gain. If I just say DC gain is 10 dB, then 10 dB is 3.16. Pick K so that the DC gain is 3.16, and you get K is 876. So there's G of S, and your answers are going to vary a little bit. Depends how you draw your graph. Where the corners are will vary with each person, but it should be something kind of like this. Something 1.8-ish, 7-ish, 22-ish. This is also one nice thing about Bode plots. I see all 3 poles. On a step response, I would just get the dominant pole. Bode plot, I get all the poles. Advantage of frequency domain. Problem 2 is repeat with this system. So again, the trick is draw in your asymptotes. This one is about plus 40 dB per decade. Over here, I've got minus 40 dB per decade. And in the middle is your 0. So here's your plus 40, 0, minus 40. What this tells you is I've got 2 poles right here. I've got 2 poles right here. The angle of the pole, complex part, comes from the gain of the corner. Gain of the corner is 1 over 2 zeta. That's gain relative to the asymptote, relative to that corner. So doing that, draw on your straight line asymptotes. There's my corner. I know there's one corner, one pole at about 0.61 radians per second. There's another corner at 19 radians per second. So I've got one set of poles here, one set of poles there. There are 2 zeros somewhere left of 0.1. Call it 0. It's off the graph. To get the angle, I look at the gain at the corner. This is plus 2 dB. So 1 over 2 zeta is plus 2 dB, 1.259. Solve for zeta is 0.39. Take the arc cosine and get 66 degrees. So this pole's at 0.61 at 66 degrees. The second pole, gain of the corner is about 8 dB. 1 over 2 zeta is 8 dB, or 2.5. Solve for zeta, take the arc cosine, 78 degrees. There's the second pole. To find K, pick any frequency you want and match the gain. I chose 3 radians per second, so at 3 radians per second, the gain should be right here. So at 3 radians per second, it should be plus 9 dB. So find K so that the gain is correct. I get K is 963. There's G of S. Problem 3. If I have a Nichols chart, I want to find the max gain for stability and K for resonance of 1.5. The beauty of Nichols charts is I don't have to model the system. I don't need to find the inductance, capacitance, resistances, inertias, inductances, or anything like that. All I need is just a gain at frequency, and I don't need that many points either. If I take data like this and convert it to a Nichols chart, here I'm going to use the Nichols chart in MATLAB, the one that is in the lecture notes called Nichols 2. It's plot the gain, well, I pass to it the gain versus frequency, g of j omega. So I'm going to convert this to gain. That'd be 10 to the dB over 20. That's the gain. And the phase shift is e to the minus j times theta, where theta is in radians, or degrees convert to radians. Do that, I get a bunch of complex numbers. Now plot that on a Nichols chart, function Nichols 2, where we've got gain, and there's my M circle, 1.5, and here's what you get. Now for max gain for stability is where you look at 180 degrees. This distance right here is the max gain for stability, about plus 7 dB, maybe plus 8 dB. To be tangent to the M circle, I want to slide this down till I'm right about here. There's the gain for stability, about minus 7 dB. Correction, that's the gain for resonance of 1.5. For that I want to be tangent. So with MATLAB, I can guess again. This is the nominal system, g times 1. Max gain for stability times 2.5. That gives me this curve. Gain to be tangent, 0.45. Gives you this curve. Here I'm tangent. Here I pass through minus 1. So there's the max gain for stability, 2.5. Gain for resonance of 1.5 is 0.45. Again, this is the beauty of Nichols charts. I don't need the transfer function. I don't need the transfer function. I don't need any modeling. I just need a couple data points. In fact, the only data point that I need is 180 degrees, this one right here, for stability, and this point where I'm tangent. If I don't know where I'm going to be tangent, that's why you take a couple points and hope somewhere in this range I've got the correct phase shift. That's a Nichols chart. Nichols charts are really useful. They kind of explain what's going on, but they're kind of painful to use. Because of that, what we normally do is design for phase margin. For designing for phase margin, what I do is take this M circle where it intersects at 0 dB. Instead of being tangent to the M circle, I'm going to force it to intersect the M circle at this point. That's a whole lot easier to design, and it's usually not too far off. So that's what the later problems look at, design for phase margin. If I design for a 40-degree phase margin, that means that at some frequency, g times k is 1 at minus 140 degrees. For gain compensation, what I need to do is find out what frequency has the phase shift to minus 140. So that's just kind of guess again, iterate until the phase is minus 140. So if you guess again, it's 5.338 radians per second. You can get that by guessing in MATLAB, or in my calculator, I've got a Newton's method programmed in. It iterates using Newton's method until the error is less than 0.001. Yeah, basically iterating. It gives you the frequency where the phase is minus 140. At that point, I want the gain to be 1, so pick k to make the gain 1. K is 1 over 0.1475, so there's k. To check your answer, a couple ways to check. One is plot the step response. What is the overshoot that corresponds to 40-degree phase margin? To do that, I find the M circle. The M circle is roughly your g over 1 plus g, 1.46. Once I know M sub m, I can find zeta. Once I know zeta, I can find the overshoot. So what I'm really doing when I design for 40-degree phase margin, I'm really designing for 28% overshoot. If I check that in MATLAB, here's my g of s, here's k, form the closed loop system, find the step response, and the overshoot. It should be 28%. It's actually 30%. It's a little bit high. The reason it's high is because when you design for phase margin, I actually intersect the M circle rather than being tangent to it. And since I intersect it, the resonance is too high and the overshoot's too high. And you can see that if I plot this on a Nichols chart. This isn't required, but it does help illustrate what's going on. Plot g times k on a Nichols chart, and notice that I intersect the M circle right here. And actually went slightly inside. That slightly inside is what causes the overshoot to be too high. So designing for phase margin is usually too aggressive. In fact, it's always too aggressive. and the overshoot is a little bit higher than 28% overshoot. Problem 5. If I want to add a lead compensator, there's a couple ways of doing it. My resonance from problem 4 was 5.338 radians per second, so put the 0 1 to 3 times that. Another way to do it is, here's the pole, keep the pole at s equals 0, there's the next slowest pole, cancel it, which oddly enough is in this range. So either way you do it, pick your 0. Once you pick the 0, put the pole 10 times further out. So there's G times K. Now, where is the phase minus 140 degrees? I'll search until the angles add up. It's now at 12 radians per second. The gain is wrong. Pick K to make the gain 1 there, so there's K. And here's K of S. Checking in MATLAB, here's your K, form the closed loop system, find the step response. I should have 28% overshoot. It's a little bit high. Again, that's because I hit the M circle. If there's your overshoot, plot the Nichols chart, I kind of see here's your G times lead. I intersect the M circle right here and go slightly inside. So the resonance is slightly too high, the overshoot slightly too high. That's, again, what you get when you design for phase margin. Again, the reason I'm doing this is actually pretty easy to do. As long as I can search and find out what frequency has a phase shift to minus 140 degrees, I can find K. That's much easier than a Nichols chart, where I have to sit there and figure out where I'm going to be tangent, and that depends upon the slope. This point doesn't change. This one does. Problem 6 and 7 says, suppose I've got a delay in the system. Now what happens? Well, the beauty of frequency domain is I don't really care. I just want to find out where is the net phase shift minus 140 degrees. Search, you get a number, 2.34 radians per second. Pick K to make the gain 1 there, and there's K. Yeah, not really that hard. That's a whole lot easier than root locus. One of the reasons some people prefer frequency domain. Check, and the overshoot should be 28%. It's actually 34%. The reason, again from the Nichols chart, is I intersect the M circle right here. Because of the delay, it pushed this curve up a little bit. So I'm actually further inside the M circle. And further inside means a higher resonance, means more overshoot. Last problem, add a lead compensator. Now this is a little bit different. Normally I'd say cancel the pole at minus 9. That's actually not correct. Back from problem number 6, the resonance was at 2.34 radians per second. I want to add a compensator that adds phase at 2.34 radians per second. So pick the 0 to be 1 to 3 times this. I chose 3. 9's a little bit too far out. If you choose 3 radians per second, there's your G times K. Find out where the phase shift is minus 140 degrees. It's now 4.7 radians per second. Pick K to make the gain 1, and there's K of S. If I check in MATLAB, I've got a faster system, but I've got quite a bit of overshoot. Again, for checking in MATLAB, I used a Bode approximation for delay. I used a 4th order Bode approximation with a 0.2 second delay. That way MATLAB could draw it. Overshoot's quite a bit higher. That's not because I did it wrong. That's because when you design for phase margin, I intersect the M circle right here. Because of the extra delay, that flattened the graph, flattened G of J omega. I'm now passing much further into the M circle. Much higher gain means much more overshoot. So in this case, I really want to back off in the gain. I really want to be tangent to the M circle, not intersecting it. And I'm assuming that the tangent point is right here. Turns out that's a bad assumption when you have a delay and a lead compensator. Bad assumption means a bad design. But that's what you get when you design for phase margin. Again, Nichols chart kind of shows why it's not working and what you have to do to fix it. So that's homework set number 12 for ECE 461.